So, uh, so today we'll talk about the 4x4 Alexander R matrix, and there will be no homework, partially because I think I said there will be about 10 assignments, and there are like 12 or 13 weeks, so, but I'm also, it's only about 10 assignments. It can be plus or minus some. And also because I've fallen way behind on marking, so it just doesn't make sense. Also, I should really acknowledge an embarrassment, but let me first explain how it's happening, but also why it's happening, but also explain about the structure of the class. So, like, this class is structured as a build-up to something hard. There is something hard we want to do, and I'm doing it step by step. So part 0 of the class was an outline of a dream. For such and such purposes, I want an invariant which will be fast to compute and have good algebraic properties and be strong. Okay? And then I'm starting to build up to that invariant, and it will be in roughly 6 steps. And we're in roughly step 2. So first of all, one idea was to use finite dimensional involutive Hopf algebras plus an array element. And then we had an example, and the example was lovely, but with difficulties, as expected. We were building up to something big. So we have to continue building. Then I had this finite dimensional Hopf algebras plus R matrix, and we're not done with the discussion. But I wanted to show an example, and the truth is, I didn't know what example to show. Like when I learned, when my personal mathematical history evolved to here, it skipped this step. So I looked around and thought that I have a cool example, and it's this curler example, and it's cool for various reasons. But the truth is that I haven't read the curler paper. I just came up with my own, what I thought was a version of it. And then several things happened. And this I did like 2 or 3 months ago when I was starting to think about this class. But then several things happened. First of all, it turned out that it wasn't the just yesterday I realized it's just not the curler algebra. It's my own thing which I came up with for other reasons, and which I assumed it's isomorphic to the curler algebra because it has the same dimension, but it's not. Second, it doesn't have all the properties I want. So it does define an invariant of rotational virtual tangles by defining its values of overcrossing and undercrossing and spinors and anti-spinors, things that spin and things that spin in the opposite direction. We actually checked that last time, but it doesn't have the other structure that I was hoping to demonstrate, namely a coproduct and an antipode. And finally, it turns out, so it was 8-dimensional, so that's why I thought it was curler. But it turned out there was an easy simplification to make that gets rid of this element k. It just wasn't necessary. So in fact, it's 4-dimensional. So it's definitely not what I was meaning to, not the demo I wanted to show, but it is a demo. And it does show things, not all the things that I was hoping it would do. Anyway, the next chapter after that, starting next week, will be actually an infinite dimensional example, the Heisenberg algebra. And, the enveloping algebra of the Heisenberg algebra. And surprisingly, even though it's infinite dimensional, so you'd think it would be impossible to compute, it's actually easier to compute. Then there will be the same thing but perturbed. Then there will be SL2, 0, whatever that means. And then there will be SL2, 0 perturbed, and that will be the success, okay? Okay. Anyway, sorry, so this is just an explanation why the example I'm going to give is lovely, but not the example I really meant to give. It doesn't really fit in the progression as I wanted. So let me remind you, we were talking about rotational virtual tangles. Given a Hopf algebra plus R, you get a meta-Hopf algebra morphisms into H to the tensor, to the meta-Hopf algebra of powers of H. And in fact, and rotational virtual tangles are the meta-monoids, so basically all ways of stitching together overcrossings, undercrossing, spinner, anti-spinner, divided out by all the relations, including this Weir relation, okay? And also including some relation of the form CC bar is equal to 1. So these two are inverses of each other. So in fact, this constructs not a morphism of So far I haven't told you what are the coproduct and the antipode, and I still need to tell you. So I told you what is multiplication, what is eta, what is the disjoint union operation, but I am yet to tell you what is the coproduct, what is the antipode, and what is the epsilon, deleting an element, okay? So these I still need to tell you. So, sorry, not deleting an element, deleting a strand. So these are defined by their action on the generators, okay? And they are defined precisely as you expect them to be defined, and they are defined so that they are morphisms of the multiplicative structure. So basically, if you apply the coproduct and then stitch, it's the same as stitching and then applying the coproduct in the appropriate way. So really all I need to tell you is how they act on the generators. For epsilon, it's completely clear. Okay? So epsilon acts on the spinner by removing it, removing its label and removing it, and it acts on the crossing. So in fact, if you have crossings, you need to tell which epsilon to apply, which strand deletion to apply, this one or that one. So if you delete strand 1, you're left with strand 2 with no crossing. And if you delete strand 2, you're left with strand 1 with no crossing on it. So really epsilon, so if you take R12 and apply to it epsilon 1, the result should be eta 2, right, etc. So this one is trivial. The coproduct is also exactly what you expect. So the coproduct acts by doubling a strand. So so if you want to apply delta from 1 to you know what, let's call this one 3. So delta 1, 2, if you want to apply it to this, you just double the strand, and then this in itself is a product of two R's. So this is really an M of two R's. And you can write you can write it explicitly, and that becomes one of the axioms for R. Okay, R should satisfy this axiom. And then, likewise, if you apply the coproduct on the other side, and likewise if you do it for the underproduct, I mean, this is all clear. And there is a slight complication with S. So S is supposed to be strand reversal. But all my strands are pointing up at the ends. So I cannot reverse strands. They will be pointing down. So S now, so what replaces S is not strand reversal. So S becomes, well, basically, so if you have a strand, you replace it by, well, you reverse the direction, but you add a little thing here and a little thing here, so that the ends are oriented the right way. Okay, so basically you add some rotations or potential rotations. Now. Roland, my collaborator on all this, is really annoyed because the conventions we ended up choosing are that S is the mirror image of the letter S. Like Roland would have much preferred it to be this way, but this will disagree with too many other conventions, so that's unfortunate. Okay? But now I have to make comments. This is, what does it really mean? It means that I'm defining S on the generators. So, for example, S1 acting on the overcrossing will become, so it becomes, sorry, it becomes this, but now I add a hook to it, and that, and if you look at it, this is what
okay.
No, sorry, I did it wrong. I wanted to do S2. Sorry. So S2 of, right, sorry, S2 of of R. So in other words, what I'm telling you is I'm computing S2 of R12. So S2 of R12 is, so now to turn it into a rotational virtual tangle, to write it in terms of the generators, I need to rotate this by 90 degrees. And then it becomes this, I believe. I hope. Yeah, it becomes that. Sorry. Yeah, it becomes that with the orientation like that. But this is just an unnecessary zigzag. It doesn't count for rotation numbers. So this is just, this is strand 2. So this is just what you would call R inverse 1, 2. Okay, so likewise you can figure out how all the versions of S act on all the versions of all the things here. Okay, and then the last thing to look at is, sorry, I still want this on. Oh, it can't recognize me. Okay. The last thing I wanted, or maybe I'll do it here. The last thing I want to look at is S squared. So how does S squared act on a strand? So first of all, S adds, reverses it and add hooks. And then S squared will, so okay, on the up-facing thing, I added a hook to the left. So S squared will take this thing and add another hook here, and on the outgoing, I added a hook to the left, and on the incoming, I added a hook to the right. Okay? So S squared will change, but now the orientation got reversed once again. So S squared will change a strand to a strand with two spinners at the end. So the last axiom, instead of S squared is equal to the identity, you have some axiom of the form S squared applied to, well, I will, instead of writing it in the meta language, I could write it in the meta language. So S squared is multiplication, stitching a C on the top and a C at the bottom. Okay? But, wait, is this a C? Yes. But I could write it as an algebra axiom. So S squared of any element of the algebra is you conjugate the element by C. So it's a weird axiom. Instead of, and that's the main distinction between a Hopf algebra and an involutive Hopf algebra. So involutive is when you have that. Now, unfortunately, the demo I have does not demonstrate this, because the demo I have simply does not have these operations. Well, maybe it has epsilon, but it doesn't have the other operations. So for this, we will have to wait for this. So really, our first full demo will be this one. Sorry. Anyway, let me go back to computations, to the demo. And as I mentioned, you know, last time I blundered and I showed an 8-dimensional algebra, but it could be reduced to 4. In fact, K is unnecessary. Yes?
Sorry, I'm kind of confused about the S squared, like S squared of X. What is X again?
Sorry?
What is X again?
So I wrote it in algebra language. So if you have any element of the algebra, so basically, you know, you write elements of the algebra on strands. So if you have any element of the algebra, applying S squared to it should be conjugation by C. Or this is, or to be more precise, this is the axiom on algebras that would make our construction a morphism out of tangles, assuming that when tangles are endowed with this structure. So if you apply S squared to a component of a tangle, right? If you apply S squared to a component of a tangle, that component gets to have two C's added to it, C inverse and C. And so you want the algebra to have the same property. So if you apply S squared to, right, any strand becomes an element of the algebra, so you want that S squared of any element of the algebra will have this property.
So then you crossed out the S squared equals I.
Sorry?
And then you crossed out the S squared
No. No, S squared, when you apply S squared to a strand, it becomes a strand with a curl at the top and a curl at the bottom, or a rotation at the top and rotation at the bottom, and rotations are not trivial. I'm in the world of rotational virtual tangles, and rotations have...
But it's a C and then a C bar.
Yeah, but in between there are other things. They don't cancel.
What is in between them?
The rest of the tangle.
But we are just reversing the strand, like there's only one strand there.
No, when I say, every time when I say double a strand, I mean double a strand in a big tangle. I'm just writing it schematically as a single strand becomes two.
Oh, I see.
Okay? Really, schematically I'm reversing the strand, but that strand lies in a big tangle, so hence I've added these extra little things. So you have a big tangle and in it one strand. Applying S to that strand means doing this to it. Applying S squared meaning adding two C's, one at the top and one at the bottom. And the C's are actually, if they were central elements, you could somehow slide them. But I never said that they are.
Yeah, this makes sense to help.
Okay?
Yeah.
Okay. So, how to get from last class to this? So basically, our algebra was the algebra generated by A, B, C, and D. And these just were the algebra of 2 by 2 matrices. They were just forming the algebra of 2 by 2 matrices. And then I added an element K. But K, you can simply substitute K equals 1 minus 1. It's just this matrix. This matrix has all the properties that K had to have. So when you do this substitution, you no longer need K, and you're just working with the algebra of 2 by 2 matrices, and K disappears from all the formulas, okay? So everything becomes simpler. Instead of an 8 by 8 multiplication table, you have a 4 by 4 multiplication table. And the formulas the definitions are the same, but the table is shorter. And then the identity element is still A plus D. It's not, I don't call it 1, I call it A plus D. So let's start this. And the basis now has only 4 elements instead of 8. Everything is simpler. I'm just silly. And then, if you don't believe me, we can check associativity. We can check that the units are units. And then the R matrices are also simpler, but they're simpler simply in that every place there was a K, I replaced it by 1 minus 1, or really by A minus D, and then simplified. So you get these things. These are the same other than that modification. And then you can check Reidemeister 3, checks. Reidemeister 2, checks. Reidemeister, the naive Reidemeister doesn't check. The corrected Reidemeister, when you insert the anti-spinner, hopefully will check. The spinner and the anti-spinner are inverses, and you check all the Reidemeister ones. They don't need to hold, but they hold. And finally, you check the whirl, everything is good. Okay? Sorry, okay. The next thing is, now I actually want to check what the resulting invariant is. Okay? So, you give me a note, and I need to compute what the resulting invariant is. So suppose the note is x4, 2, 5, 1, x, 2, 6, 3, 5, x, 6, 4, 7, 3. So by the way, this is a long knot. It is not. It's a strand, which is an open strand, but right, because it starts from 1 and ends in 7, rather than closing again to 1. So it's not okay. It's a knotted interval. Anyway, I mean, you can probably guess what this knot is, right? It has 3 crossings, so what could it be? Okay? It better be the trefoil. Okay? So you know, you can draw the trefoil and then figure out what are, rotate all the crossings so that they're all all the strands are pointing up at the crossings, then figure out what the rotation number is in, and get the answer, and get the computer to spit out the answer. This will take you probably 15 minutes, okay? At least, okay? And there are, well, and I really want to compute in mass, right? I want to compute, 250 knots, say. I can't do it by hand. I need to figure out how to do it, how to automate this. So I need a storage format that will store rotational virtual nodes. And I need to automatically convert from this to that storage format. So the storage format is actually this is a long trefoil, so it looks like that, I think. Wait, no, wait, sorry. 1, 2. Wait, God, I used to know how to draw a trefoil, but I forgot. Okay, okay, oh, so. Okay, this is better. Okay, good. Remember that in my numbering system, every edge is numbered. So this is 1, 2, 3, 4, 5, 6, 7. I don't know if the numbers match, but maybe better if they, well, okay, they do, yeah. Anyway, so my storage format for the way I will want to store this information is by storing a pair of things. So I will want to write it as RVK, and then a pair of things. The first one should be a list of crossings. So the first crossing is a positive crossing. The second, in fact, all of them are positive. So 3 positive crossings, but in principle they could be negative. And also, for my current purposes, I don't want to know the 4 labels around. I just want to know names of strands. Okay? And each crossing should have just the 2 names of strands that appear in it. So I will decide that so at a crossing, I name the strands by what their name was before the crossing. So this is a crossing in which strand number 4, right, I came in from 4, goes over strand number 1. So this is a positive crossing X41. This is a positive crossing of 2/5. And this is a positive crossing of 6/3.
So 4-1, I think is a negative crossing.
What? Is it
4-1?
negative? Oh,
Yeah.
so I drew the wrong trefoil. Okay. Okay, fine, but it doesn't matter. Let's call them negative. Okay. And then I need rotation number information. So the rotation number information will be a list of all the rotation numbers on all the strands. So I don't know what they come out to be, but basically it should be a list of length 2n. I'm dropping the last strand because it will turn out that the rotation number on it is always 0. And then I just give you, rotation number 1, -1, 0, 0, 1, 7. Okay? And the question is how to automate going from here to here. Okay? So I mean, here I did it by drawing, but I don't want to actually draw. Okay? So how will I do it? Okay. First of all, figuring out the crossings is easy. So, you know what? I will not even bother. I will just go. No, I will do it. So figuring out the crossings in this notation is easy. So basically, if you have a positive crossing, it's going to be labeled I, J, K, and L. And the corresponding notation here will be X plus L over I. And if you have a negative crossing, this is a negative crossing, it's going to be labeled I, J, K, L, because remember I start my labeling in this PD notation by labeling the incoming understrand. So this should be becoming X minus of this is J over I. Okay, so basically I have to apply this rule. And how do I know if it's a positive crossing or a negative crossing? So the first index always corresponds to an incoming strand. And then if J is greater than L, then it's a positive crossing. And if and otherwise, if J is smaller than L, it's a negative crossing. Okay, so it's stupid, but you have to do it. So let's look at it here. So here the incoming strand is number 4. So this is I, J, K, L. J is smaller than L, so that's a negative crossing. What? J is smaller than L?
J is bigger than L.
J is bigger than L, right, sorry. 2 is bigger than 1. So J is bigger than L, so this is a positive crossing, and the corresponding indices are 1, 4. And then this is a, you know what, I don't know, it doesn't, no, I will finish it, sorry. So here J is bigger than L again, so this is again a positive crossing, and the indices are 5 and 2, and this is again a positive crossing, and the indices are 6 and 3. I hope this is right. Yeah, so it's what I wrote here, but with the sign split. This was a mistake. Or this picture is not the right picture. But now how do I recover the rotation numbers? So I draw the knot as much as I can. Yes?
So which numbers come first? Which of the numbers will come first? With the I and J,
Sorry?
The numbers, which will come first? Should it be, in the middle one, should it be 2, 5 or 5, 2?
Oh, is it 5 over 2? No, it's 5 over 2, yes.
Oh, okay.
I mean, it's, the first number is the over, so again, the rule is IJKL in a positive crossing become L up after XLI. But again, these are technical details.
Yeah.
This is really technical. The hard thing is how to figure out the rotation numbers. So the way I will figure out the rotation numbers is I will start walking along the knot. I will start walking along the knot, and as I walk along it, I will draw in the plane whatever I can in a way consistent with the rules of rotational virtual knots, namely, I will I will try to draw all the crossings so that all the strands are pointing up. Okay? So, in other words, so what I'll have is I'll have a front line, and I'll start adding more and more stuff to it, and it will start by having strand number 1 at the bottom pointing up. Okay? And then I walk on strand number 1. I walk, and I see that I cross strand number 4 in a positive crossing where 1 is over. So, if I want to draw the next vertical, you know what, maybe I should switch colors. So that this is not a part of the knot, this is just in my imagination. So, for the next step, 1 goes undisturbed, and 4 goes under it with in the positive direction. So, in other words, 4 should go this way. But this is drawn badly because not both strands are pointing up here. So really I should be drawing it this way. I should be drawing it like that. This is strand number 4. Okay? So so strand number 4 goes up, the numbering here becomes 5, the numbering here becomes 2, and now both of them are positive. But you know, I'm a computer. I can't keep this picture in mind. So what I will remember from this picture is the sequence of numbers 5. So this picture really corresponds to the sequence of numbers 5 to 4. But also, it would be handy to know that this is an incoming 4 and this is an outgoing 5. So I'll indicate incoming with minus signs. So this is the sequence 5 to minus 4. And the sequence corresponding to what the original picture was just a plus 1. Finally, let me keep a record of what rotation numbers do I already know. Okay? So rotation numbers should be a list of 6 numbers. And when I start, I know nothing. When I come to the next step, 0, 0, 0, 0, 0, 0, let's see. Strand number 4, well, did it rotate or did it not rotate? So my convention will be that you can measure rotations by the times when the tangent is pointing in the positive direction. So every time a tangent will be passing into, will be crossing the positive direction, I will count. So here, strand number 4, well, the tangent is pointing in the negative direction. So I don't, this is the rotation number on strand number 4. This is the fourth 0. But I don't need to say it, because I don't need to add to it or change it, because 4 didn't do anything. Okay, next step. So I continue walking along the knot. I go on 2, and I find that 2 goes under 5 in a positive crossing. So you know what? Let me try to be a bit more compact. So 2 will go under something. So now 5 goes above it, and it's in the positive direction. It means it comes from left to right. But again, this is drawn incorrectly. I should be drawing it this way. Okay? And this is, again, 5. And this will be 6, and this will be 3. And the picture I have now is, so I have an outgoing 5, an incoming 5, a 3, a 6, and a negative 4. And here, on strand number 5, I collected a negative contribution to the crossing number. No, a positive. This is, the tangent is turning counterclockwise. So here it will be 0, 0, 0, 0, plus 1, 0. Okay. Then, I guess my convention is not to worry about the fact that there is a 5 and a minus 5 here. 5 and minus 5 just means that the two will connect. I mean, my convention is to wait and connect them only when my walk gets to number 5. And it hasn't yet. I'm still just at number 3. Okay? But that's just a programming decision. So, I mean, instead I could connect now. And then the next step, in the front, the 5 and the minus 5 cancel. So I have 3, 6, negative 4. And I've added a negative rotation to 5. So the rotation numbers are 0, 0, 0, 0 again, 0. This one got canceled. And indeed, you know, you get kind of a zigzag here, which, okay? Next, I walk from 3 on. So 3 goes under 6. What? What?
Should be the
What? Sorry?
Because it's 1, 4, 5, 2, and then you go 6, 3 instead of 3, 6.
Sorry?
Should the, like, on the label of like the original labeling you had with the X's with none of the pluses
Oh,
around
here?
that? Yeah. Should it, because it's a positive crossing, shouldn't it be the last number first and then?
Oh, you're right. So this is a 6, 3, 3, 6. Right, sorry. So now 3 goes over 6 in the positive direction. So actually, I mean, all of these just continue. And now I'm doing the next step. And the next step is 3 goes over. So 3 is uninterrupted. There is a 6 going like this. This is a 6. This is a 7. And the front now reads 7. Oh, sorry, this became a 4. So 7, 4, 6, minus 6. Sorry, negative 6. -4, no, 6 and then -4, okay? And now, in the next step, and the crossing number and the rotation numbers have not changed, so they're still 0, 0, 0, 0, 0, 0. Then in the next step, I know that I have an adjacent -6 and 6, so I connect them, and meaning just remove them from the front. But you see, I also add so this is subtract 1 from the 6th place in the rotation number, so I'll have a -1 here. And then 4 connects to 4, so I have to subtract 1 at number 4, and this is the output, I believe.
Isn't the tangency like
Oh,
6
no,
continuing
for
up?
6, oh, I'm wrong. For 6, the tangency is to the left. So this doesn't count. So this is the correct answer. And this is, okay, this is going clockwise, and this is going counterclockwise, but it's actually tangent in the wrong direction. Okay, so basically but this could be automated. Okay, so here is the program. Here is the program. Okay, so you know, it's again, I don't want to go through the mathematical syntax. I want the main point to be visible. Okay, so basically, I start by initializing the front to be just the number 1. Then n is the length of the number of crossings, and then the rotation numbers is a table of 2n zeros. And then I make a list of crossings, and I just get it from the PD, but every time I see if x is positive, so the test whether it's positive or not is built in. So if I see a positive x, I replace it by xp li, and if it's and otherwise, I replace it by xm ji. That's the rule that was written there. And then I walk along the knot. So as k goes from 1 to 2n, I walk along the knot. And the first thing I do is I print the current value of k, the front and the rotations, just for the demo. I don't need to print them. I'm printing them so that you could compare with what's written here. Then if the front does, so I'm at k. If the front has a negative k in it already, it means that I'm looping back, and I need to connect it. But so first of all, if the front is free of negative k, then if I see a positive crossing where k is over, or a negative crossing where k is under, I change the front to be whatever is written here, but this is the automation of what I just did here by hand. If it's a positive crossing with k as the understrand, or a negative crossing with k as the overstrand, then I replace k by a triple of numbers, again, which are determined by exactly the same way, but I also add 1 to some rotation number. That's this plus that adds 1 increments. And finally, in the other case, if I'm hitting back, then if I go from k to minus k, I'll subtract 1 from the rotation number. And if it's from minus k to k, I don't need to subtract anything because it's heading the wrong way. So that's the sketch of so I told you what the program does, and I outlined how it works. So let's enter it into the computer. And actually, well, this is not necessary. That's just usage information. But let's do an example. So this is, I hope, the same notes that I entered. And here are the intermediate printouts. And, is it the same? Well, okay, there are more, it's not exactly the same because I went through things in a different order. Okay, but that's, I think that's the point. That's, well, yeah, I'm out of time. Well, to be continued, I don't know what to say. Sorry, you know, it's all very, very, very technical, but that's life. Sometimes you have to do technical things, and believe me, like, this might look, I don't know what it looks to you, but had I asked you in a homework question to write this conversion program, you would have found it extremely difficult. It's actually very, very hard to, I mean, it takes a few days of concentration to come up with such algorithms. It's harder than it looks. Anyway, see you on Monday.